Okay, let's get started. So I'm recording this video because we missed the Thursday class. Okay, so I'm recording. So I hope everyone can watch this video before the next class. So in the previous class, so we learned about the basic concept of instructions in computer systems. Okay, so I hope everyone can understand the conceptual view of a processor and instruction and then the result of instruction. So as I mentioned, actually the high-level language code is translated into the instructions, right? And then actually the machine code or machine instructions. So a CPU or a processor receives the instructions from memory. So actually the CPU reads instructions from memory and then instructions are executed one by one. Okay. And then software view, and then as I mentioned, each instruction generate the result defined by instruction set architecture, right? So, and then I also mentioned that the result generated by an instruction is change of states. And what is the change and what are changed? The data. The data in architectural states, and then the architectural state represent register files and main memory. So instructions change the data in register files or the data in main memory. So you actually you can understand the instruction and then the result of instruction like this. So actually this is the software's view to the processor and then software's view to the view for how the instruction is executed by a processor. Okay. So, and then I mentioned that we will learn about the RISC-V instructions, right? And then RISC-V is an open source instruction, and then this is an RISC type instruction. Also, the RISC-V ISA is a modular type ISA, which means that actually the baseline ISA of RISC-V is RV32I, or 32I, or 64I, or 128I. Actually, these numbers, like 32 and 64 and then 128, represent the bit width of data or address. Okay? Well, actually, it is a register. But you can understand that this number represents the bit width of data or address of a computer. So, for example, so the most current processor is a 64-bit computer processors. So, which means so these processors handle 64-bit data in default. Okay, and then but in this course we will learn about the 32-bit ISA of RISC-V. So, which means the the typical the size of the typical data is 32-bit. Also, so we can add some additional instructions if required by adding some extensions of RISC-V. So these are examples of extensions. Okay, and then we compare the RISC-V with other ISAs. Okay, okay. And then we learned how the high-level language code is translated. And then I mentioned that so we are using stored program computers. So what does that mean? The instructions are also stored in a memory, the main memory. Okay. So this is because as I explained, as you can see, the instructions are also kind of digital signals or digital data, and then these instructions, also including the real data, instructions and data are stored in main memory of a computer system. Okay, so like this, and then also I mentioned that the address of instructions is called a program counter, right? So program count. So so actually, so because instructions are in the main memory, and then a CPU reads instructions from memory. Then how a CPU uses address, okay, addresses. Okay, so which means that the address is given to the memory. So this is very basic knowledge. Address is given to the memory, and then the CPU can receive data stored in the some space some a specific space in the memory pointed by this address. Okay, so the PC or program counter is an address of instructions. So this is the example. Okay, so and then we also learned the what are stored in the memory. So obviously the instruction is stored. So instructions are stored as text data, and then also global and static data are stored in the memory. Okay, so then the intermediate data or dynamic data are also located in the memory, and then a program or CPU can read and write data in the memory, right? Then also we learned how to calculate the size of a memory. And then you need to remember that we use byte address. So which means address 1 is mapped to the 1 byte space of memory. So what is 1 byte? It's 8 bit. Okay. So the address 1 is associated with the 8 bit data space in the memory. Okay. So you can understand that the memory is very large array. Then using an address is the index of this large memory, a large array, right? So if we just use, so we can use indexes to read data from arrays, right? So like this, so we can use addresses for reading and writing data in memory, right? Okay, so this is the some example of RISC-V memory map. So uh, when a program, okay, so in on a Windows operating system, we can click, okay, we can click the icon, but actually on Linux or also on the command line interface of Mac operating system, and then in order to execute a program, then actually we need to type the name of a program, such as ls. ls is the name of a program, and then we can enter this program name on the command line interface. So what does that mean actually? Then operating system execute this binary file. So binary file. So compiled file. So if we compile high-level language code, then binary file will be created. And then in order to execute this binary file, we can just execute this file using the file name. So which means the operating system execute this binary file. So when the binary file is executed, then this memory map, the memory map is also created by the operating system. So what is the memory map? The memory map defines the range of address for specific data. So this is the example. Okay. So this is the address, then this is the data in the memory map. So you can find that the address of memory. So then you can also find the text area, the global data area, or dynamic data area, or operating system area, and the exception handlers. So I mentioned that the text part includes the instructions. Okay, so it means that the text data, well, the machine instructions are stored in this region. Okay, and then this is the address of this region. So by adjusting the program counter value, then we can access instructions. Okay, so you can find the range of the the range of addresses for the global data space. Okay, so global data, so global data or static data can be stored in the memory map, also the binary file. So the binary file is executed, then this data can be allocated to the memory. And then we can also generate the dynamic data, right? Also in C, so we can create the dynamic data area. Okay, so this is the address space for the dynamic data. So the memory map also includes some space for the operating system code. Okay, so this is the kernel area. Okay, now let's see the example. So this is the very simple C code. So right. So you can find the function. So function, uh, the function name is func, and then this function receives two arguments, right? The integer a and then integer b. So this function receives two integer data from when this function is called, right? And then this is the behavior of the function, and then the result the result will be returned. Okay, and then also you can find another function, but this function is special function. Why? So you can the name of this function is main, right? Why is this special? So in C, when a binary is firstly executed, then the main function is firstly executed, right? So if you took the C programming course, then I believe you can understand this, right? So main function is firstly called, and then inside the main function, then the variable are uh, declared like f2, f equal 3, okay? And then the function is called, right? So because this func function is called, then this code is executed, right? So this is the high-level language code, and that this is very simple code. And then using C compiler, that we can compile this code. Okay, so let's see the generate assembly code and then binary code. It means that binary code includes machine instructions, right? Or you can find the address, and then also you can find the machine code. So these are actually the instructions stored in the binary file. And then also you can find the assembly instructions in the right side. So actually we will learn about these assembly instructions of RISC-V. Okay. And then this is label. Okay, it's a label. So actually the label represent the address of this line. Okay, and then you can find that the label name is func. So what does that mean? This is the start point of func function. Okay, then what is the address of this start point of this func function? The address is 10144. Okay, so I mentioned that this address is hexadecimal code, right? Because the, the binary number is so long. Okay, so that's why we use hexadecimal numbers frequently. Okay, so machine code is also represented in hexadecimal numbers, right? Okay, so this is the first line of the func function, and then also this is the first instruction. Okay. So actually, once this first instruction is executed, then instructions are executed one by one. So how? Actually, the CPU changes the PC value, right? So this is the address of instruction, and then I mentioned that this is the program counter. So a CPU changes the program counter value, then CPU can read the corresponding instruction from the memory, and then the read instructions can be executed by a CPU. Okay, so also the you can find the main function here. Okay, you can find another label main. Okay, and then this is the address of the the first line, the first instruction of main function. So actually this is the machine instruction. Okay, and then main function actually calls the func function. So actually this is the call. So we will learn about this instruction later. So but in this example, I hope you can understand how the instructions are executed in a real computer system. Okay, so it is because the instructions are also stored in the memory as a machine instruction. Okay, and then by changing the PC, the program counter value in a CPU, the CPU can read instructions from memory, and then the CPU can execute the read instructions, and then create the result of instructions. Okay, so actually, so the two argument is assigned, and there is a call function. Okay, so actually, so this C code, this C code is translated into this RISC-V assembly code, and then the assembly instructions can be encoded to the machine instructions one by one. Okay, so this is the example, and then this is the an example of the memory map. So if you see the this value, then you can find that these values are identical to the machine code. Okay, and then this is the address. So this is the address of this machine instruction. So you can find that the address of this instruction is 000100180, right? Okay. So and then what does it mean? So this actually you can find that this is the address of the first line of main function, right? Then the instruction of the first line of a main function is FF010113. So let's see okay, you can find that the instruction is identical, right? So the instructions are stored in the memory like this. So firstly, because when this binary file is executed, then the PC is set to the first line of main function, right? Because then this address uh, is in the binary file. Okay, so this instruction is then the CPU reads this instruction FF010113. So this data is read from the memory, and then this instruction is executed by CPU, and then the result is generated. After that, the next instruction, this instruction is also read from the memory. Then how? Obviously, this PC value is changed to which value? So what is the next address? The address of this instruction. So you can check this slide. So actually it's the 10184, right? 0x. Okay. Then why? So you can find that the difference between uh this address, so this PC value, and then this address is 4. Why? Why is this difference 4? So if you read this data is FF010113. Then so this is the hexadecimal number, right? And then what is the number of digits in this number? So 8 digits, right? So what is the pin number for such 8 digits of hexadecimal number? Each digit of hexadecimal data is equivalent to the 4-bit of binary number. So it's 32-bit. So what is the size of 32-bit? This is the 4 byte. Right. So 1 byte is 8-bit, right? And then I mentioned that the most computer use byte address, right? So which means the address 1 is mapped to the 8-bit or 1 byte space in the memory. So because this data occupies the 4 byte of space, the next instruction, the address difference between this next instruction is 4. So do you understand? So also in order to read which means in order to read this instruction, the PC of the CPU is changed to the 10184, okay, 0x000. Then using this PC, then CPU reads this data. And then for the next instruction, also the 4 is increased. So the PC value is increased by 4. Then the CPU can read the next instruction. So you need to understand this. So because so in this course, we will learn how a CPU execute instruction, and then we will learn about the hardware architecture. So which means we will learn how the hardware of a computer system really works. Okay? And then, so you need to understand how the instructions are read from the memory. And then the CPU uses program counter value. And then by changing the program counter value, then the CPU can read the instructions. Do you understand? So this is important. Okay, then that's okay. So I hope everyone can understand this. Okay, so now let's see how the high-level language code is really compiled. So this slide shows the compilation process from the high-level language code to the machine instruction. So using a compiler, then if you use the Linux, then you can use the GCC. GCC represents the uh, GNU C compiler. So using the GCC, then we can compile our C code. Okay, then compiler generate the assembly instructions. Okay, it's compiled. Then usually the extension of the C file is .c, and then the extension of the assembly code is the .s. Okay, so and then the C compiler, using the assembler, the C compiler generate the object file. Okay, is the extension, the file extension of the object file is usually .o, .object, .o. Okay, so actually in the object file, the binary code, so which means the machine instructions and then the static or global data and then some other information, required information is included in this object file. Okay, so usually if you execute the C compiler, then C compiler just generate the .o file, the object file. Okay, then actually in order to execute some functions, so like the standard functions, then this C file requires the binary code or binary code for some functions. For example, we can use the printf function in our code, but so actually not to use this printf function, then we need to include the standard library, the C standard library. So this standard library includes the object file for this printf function. So actually, in order to use this printf function, then other object file, the other object file of the standard library needs to be included. Right, obviously. So this object file includes the instructions for executing the printf functions, right? So object file needs to be merged, and then this process is called the linking. Okay, and then it is done by linker, and then the binary file. Finally, the binary file is generated. So if we do not use any option, then a.out is generated, right? Then by executing this a.out, the binary file, then we can execute our code. Okay, so which means our code is assigned, allocated to the memory by an operating system, and then the CPU can execute the instructions in the memory. So this is how our program or our program is compiled, and then how our programs are executed in the computer system. Okay, so object module, like the object file, is the .o file, includes the some these data, like the header, the text segment, like instructions, right? And then, as I mentioned, static global data, and then some information, and then symbol table, and then debugging info. So this information is included in the object file. Okay. Then the linker, as during the linking process, the linker uh, merge our object file with the other object files. Okay. Then linker just can merge the segment, so which means that the binary file, the object files are merged to generate the binary file, and then also the location, some label, and then the address information can be changed. So, which means actually we can the binary file includes can include this information. So actually, we did not learn about the virtual memory, but actually this memory map is the virtual memory map, not the real memory. Okay, and then this virtual memory is managed by operating system. Okay, so but because we do not learn about the virtual memory, just ignore. So but just remember that this memory map is the virtual memory map, but okay. So just remember, but okay, we will learn about the virtual memory in chapter 5. Okay. Anyway, so you can just think that in the binary file, so this memory map is information is included in the binary file. Okay, then loading. So loading means that this binary file is executed. So like the a dot is if the a dot out binary file is generated by GCC, then by typing a dot out, then we can execute our binary file. Okay, the operating system reads the binary file information, then the binary file is allocated in the memory using this process. Okay, so and then so by assigning the virtual memory map in, uh, by the operating system, then as you can see, firstly, the, the CPU calls main. Okay. Okay, so then the binary file is loaded into the memory, and then the CPU execute instructions in the memory. Okay. So detailed process, I believe that you can learn about the more detailed process in the operating system course or compiler course. Okay. Okay, we can use the dynamic linking. Okay, so then let's see the effect of compiler optimizations. So this graph shows some uh, performance and some information for different compilation options by GCC compiler. So GCC, as I mentioned, the GCC is the GNUC compiler, and then we can use this GCC, this GCC compiler on Linux operating system. And then using the -O option, -O, then some numbers, okay, -O, 0, 1, 2, blah, blah, blah. Then we can set the optimization levels of GCC compiler. Okay, so the first graph shows the relative performance. So which means that we just set the performance of no optimization as 1, then just compare the performance of our optimization options. So the relative performance of no optimization is 1, then you can find that if the if an optimizations are applied, then the performance can be improved. Okay, so what does that mean? Compilers. So compilers are also important for the performance of our computer system. Okay, then let's see why the performance is changed. So how can you measure the performance? It's the instruction count by CPI multiplied by TC, right? But TC is the same because we run these binary files on the same computer system, and then TC is just the hardware part. So we can just compare the instruction count and CPI. So let's compare the instruction count. So no optimization is the instruction count is very large, but as you can see, if we apply some optimizations, then the instruction count is reduced. But you can observe that if we apply the O3, then so it is deeper the optimization levels, then the instruction count is slightly increased compared to the O1. Okay, the clock cycles are just it's the inverse of performance, right? Okay, then the instruction is number of instructions is increased using the O3 option. Then why? Why is the performance is why is the performance improved? So we can compare the CPI. So as you can see, the CPI is reduced with the O3 option. So these results show that the compiler optimization is critical for the performance of a computer system. Also, this slide shows some other effect. Okay, so we can use the other programming languages such as Java, and then also we can use the different algorithm. Okay, so for the bubble sort algorithm, so there are different type sorting algorithms such as the bubble sort. So this is the very uh, default, okay, the default sorting algorithm, and then we can also apply the quick sort. This is the more advanced sorting algorithm, and then we can apply. We can write a code using C, and then we can apply some different compilation options, and then also you can use Java. Okay. Okay. So this first graph shows the relative performance. Okay. So it's the same. So it's a C, but if we use the Java virtual machine, right, the performance is so low, right? But if we use the Java just-in-time compiler, so which means that the binary file is directly generated from the Java compiler, then performance is high. Okay, it's lower than the performance of C code, but it's so high compared to the Java in Java virtual machine. Okay, for quicksort, so we can find that the performance is increased, and then so and then we already know that the quick sort is faster than the bubble sort. So as I mentioned, the compared to the bubble sort, the quick sort is the advanced uh, sorting algorithm. Okay. But this graph shows that if the algorithm is changed, then the impact by the compiler optimizations can be different. Okay. Okay. So compiler optimization are sensitive to the algorithms. Okay. And then so also the algorithms are so critical. Okay. Nothing can fix a dumb algorithm. So that's why we need to study algorithms, right? Okay. Okay. And also these results show that compilers are also critical for the performance of a computer system. Okay. Okay. So until this slide, we learned how the high-level code is compiled and then how instructions are generated and then how the generated instructions are executed by a CPU. So, it may be a little bit tricky because, so as I mentioned, so we are not familiar with how hardware works. Okay, because we cannot see uh, the behavior of hardware, right? So we can just see the result from software, right? So that's why. So that's the reason. But in this course, you need to understand how instructions are executed by a CPU. So it is so important. Okay. Okay. So now let's learn about the instructions, the detailed RISC-V instructions. Okay. Okay. So ISA design uh, principles. Okay. Okay. So so David Patterson and John Hennessy invented actually and then their students. So uh, they invented RISC-V, and then these are some principles uh, of the RISC-V design. Okay. So simplicity favors regularity. So which means that uh, in order to make the simpler instructions or the simpler hardware, then we need to consider regularity. Okay, and then make the common case fast. So I hope some students remember this. Okay, so this is the one of 8 great ideas, in computer architecture, right? And then smaller is faster, obviously. In the hardware, smaller is faster. Okay, good design demands good compromises. Okay, so these are some uh, principles of ISA design. Okay, so let's start from the arithmetic instructions. So what then arithmetic instructions are used for performing arithmetic operations. So what are arithmetic operations? Addition, subtraction, multiplication, and division, and then some other uh, operations, arithmetic operations. Okay, so RISC-V. So actually, the very basic form of the arithmetic operation is A equal E plus C. So, so in this operation, so we can say that, oops, what is this? So these are operands, okay? And then what is this? This is the operator. Then what can you observe? Actually, in this very simple arithmetic operation, so we can observe that two operands are computed by operator, the specific operator, and then the result is generated. So this is the simplest arithmetic operation. Okay, and then the RISC-V just support this simple arithmetic operations. Okay, so we can define these operations using assembly instruction like this. So it's a plus that it means represent the add operation, and then A is the result. So it's a result, or it's called the destination, right? And then B and C are source operands. Okay, and then it represents the A equal B plus C. So it's just a definition, right? So we we just define, oh, A equal B plus C. It can be represented using add A comma B comma C. Okay. And then for other operations such as A equal B minus C, then we can just define another operator, sub, another instruction, sub, and A, B, C. It's the same form, right? And then we just define the very basic operation, the arithmetic operation. So we may define A equal B plus C plus D, but this form is not defined in RISC-V. It is because we can just make this operation using two very basic instructions. Okay, so design policy, design principle one, the simplicity favors regularity. So which means all arithmetic operations, all arithmetic instructions have the same format. Okay, and then why do we use the regular representation? Because that's for simplicity, and then simplicity enables higher performance at lower cost in hardware. So when we write a code, we do not consider about the hardware, but actually, so our instructions are computed by hardware. So which means we need to consider hardware. Okay. So when the RISC-V is designed, this principle, so simplicity favors regularity. This principle is considered for what? Simplicity enables higher performance at lower cost in hardware. Okay, so this is the example. Okay, so this is a C code, and we can represent the C code like add A comma B comma C. So add is the instruction. So but it's actually, as I mentioned, the CPU cannot understand the alphabet letters, right? So this is mnemonic indicates. Okay, so it's a mnemonic. Okay, so we just represent this instruction using the word add. Okay, and B and C are source operand, and A is the destination operand. Okay. Subtraction, as I mentioned, the subtraction has the same form, and then but the mnemonic is changed. Okay, so this part is changed, but the form, overall format is the same. Okay, so simplicity favors regularity. The same number of operands, so the format is the same, and then same number of operands. The two sources and then one destination. Okay, why? It's good for the hardware. Okay, So this is another example. The C code is A equal B plus C minus D. Then by using two instructions, you can implement this C code. Okay. So because in this C code, there are three source operands, but in the RISC-V instructions, we cannot use three operands. But simply we can use the two instructions like add and sub. So by doing this, we can implement this C code using RISC-V instructions. So make the common case fast, okay? Because the RISC-V employs only simple and commonly used instructions, okay? So the hardware is simpler. So so this is also the feature of RISC type instruction, or okay. So you may think that then x86, though it's a CISC time instruction. The RISC x86, the hardware is not x86 is not good for the hardware design, right? It may be true, but so as I mentioned, actually the x86 CPU, the current x86 CPU uh, employs the RISC-like architecture. Then the complex instructions are just translated into the simpler instructions. Okay. Okay. So we learned the very basic arithmetic instruction add and sum. And now, so we will learn about the operands of a CPU, the registers and immediate operands. So, operands are data used by instructions, right? So for example, add A comma B comma C. So these A, B, C are operands used by add instruction. So we can say that these are operands. Then what are operands? Operands are just data, right? So data processed by or computed by instructions. We can call these data as operands, right? So in a CPU, then we can use three types of operands. The data in registers. So if you remember the concept of a processor, then we can find that the data in registers are changed. So the registers, okay? So it's the same, okay? And the memory, the data in memory, and constant. The instructions can use constant data. Also, this constant data is called immediate. Okay, so these are three main types of operands used by instructions. So let's learn about the registers. So we learned about the arithmetic instruction like add and sub, and then we represent the add instruction like add A comma B comma C. So these are operands. But actually, CPU add instruction just use data in registers. And then, RISC-V, the register data is represented using X and the number. So this number is the register number. So we can represent this instruction like the X add, X1, X2, or X3, comma X3. Okay, so arithmetic instructions such as add or sub instructions use register operands. Then, what are registers? The registers is the small data space or memory, because we store data in the memory, or small data space in a CPU. Okay, and then actually the CPU use the small space for the registers, and then the number of registers. The number of registers are defined in ISA document, in the ISA. So for example, the RISC-V has a 32 bit register file. What does that mean? So this number 32 bit represents the size of a single register. And then there are 32 registers. So 32 bit is the size of a single register, and then there are 32 registers. So which means RISC-V has the registers. So from X0 to X31, because there are 32 registers. Okay. And then the CPU stores the frequently accessed data in the register file. And then this is very, very fast. Okay. Because why is it fast? Why is it fast? It's small. So compared to the main memory, the register size is much smaller. So you can actually calculate. So there are 32 registers, and then what is the size of a single register? It's 4 byte. So topic is 32 bit. So actually the register file size is the 128 byte. Okay, so small. Okay, so and then we are learning about the 32-bit computer system. So and then which means we are learning about the IV32I. So I mentioned that this 32 represents the size of a single register file or size of a typical data. Actually, this number 32 is identical to the size of a single register file is 32 bit. Okay. So which means if we use the IV64I, then the size of a single register file is 64 bit. Okay. So smaller is faster. So I also copied the definition of a register. So from the Wikipedia. Okay. So quickly accessible location in a CPU and then small amount of fast storage. Okay. So small and fast. And then you can find the some you can understand the register like this. Okay. So the register is also the very small memory. And then I mentioned that you can understand the memory like the array. Okay. Then each element can store data. So this is the structural view of the register file. Okay, so there are 32 registers from X0 to X31 right here. So by using this register number, so we can access the corresponding register in the register file. And then the so XLEN represent the size of a single register file. So actually this represent the bin number. So for the 32-bit computer system, like so it is supported by IV32. So supported by IMV 32I, then XLEN is 32. Okay? Okay. So also there are 32 registers. Then also the CPU has the PC register. The PC register just stores the program counter value. So by changing the value in the PC register, the CPU can change the PC value. That can be, so which means the address of the instruction, which will be read from the memory. Okay. Okay. And also in the RISC-V, X0, the value of X0 is always 0 or 0, right? Always 0. Okay. So it's not changed. We cannot change it. It's always 0. The output of X0 register is always 0. It's a special purpose register. Okay. Okay. Also, uh, when you write on RISC-V assembly code, so we can use the register numbers or we can use the ABI name. Okay, so this represents the same register, but RISC-V, some registers have a specific purposes. Such, for example, X0 register. X0 register is called 0 because the output of the X0 is always 0. It's a constant 0. And then X1, the register X1, we frequently use the register X1 as the return address. So we learn about the return address later. So then instead of X1, then we can use the ABI name like RA. So just RISC-V assembly code, we can use the register number. Also, we can use the ABI names. Okay. Okay. So let's see the example. So this is the C code, and then this is the compiled RISC-V assembly code. Okay. So unlike the previous example, was add a comma b comma c, but instead of a comma b comma c, we used the S0, S1, S2. So these are registers, right? S0 and S1, S2. Where is the? So you can find the S0 here, S1 here, and then S2 here. Okay. So S represents the saved. So it's equivalent to, by the definition, S0 equal S1 plus S2, right? But X1 and X2 are actually X9 and X18, and S0 is the X8. Okay, so it's equivalent to add X8, X9, X18. What is it? Okay, so So just to remember that the arithmetic instructions just to handle the data in registers, registers. Okay. So actually the C code is translated. Then we this instruction use registers. Okay. And then in this example, the sharp mark indicates the single line comment in the RISC-V assembly code. And then we can use the C code like this, A equal P plus 6. So this is the constant number. And in order to support this constant number, the RISC-V supports the immediate instructions. So you can find the add I instead of add. So I represent the immediate. Okay, so what does that mean? This means S0 is equal to S1 plus 6. So immediate operand means that it's the constant data. And then this constant data is specified in an instruction. So it means this constant data is included in the instruction, right? So why do we, so then why? Why do you use immediate type instructions? So we can uh, use the code like this. So like, for example, so move S2 some value 6 and then add S0, S1, S2. Okay, so it's equivalent code. So it means that the 6 is stored in the S2 and then we can use the add instruction. But instead of this, we write the code, we use the immediate instruction like add I, S0, S1, and 6. Why? What is the benefit of this immediate instruction? We can reduce instruction count. So, execution time is the instruction count and CPI, TC. Instruction count is also critical for the performance. So, because we can use the immediate instruction, this C code can be compiled into only one instruction. So which by doing this, then we can reduce the number of instructions. Also, another observation is that this small constant number is frequently observed in our program code. Okay, so if we define the the instructions that can handle this small constant number, then we can reduce the instruction count, and then by doing this, we can make the fast computers. Okay, so small constants are common. Then by doing this, we can reduce the actually load instructions because the data initial data is in the memory instruction memory, and then in order to read the uh, use the data in the memory, then we need to use the load instruction. Okay, so with that we will learn about the memory operands. Okay, so I will stop here because the memory operands are also the another important operands. So among three operands like registers and memory and constant, we learned about the registers and constant, the immediate value. Okay. So I will stop here, and then I hope everyone can watch this video before the next class. Okay. Thank you everyone, and then see you in the next class. 감사합니다.